Chapter 8, Section 8.1, Question P2, and we're getting into confidence intervals here. In other words, since we don't know what an actual population parameter is typically, all we have is the data from our sample. We use the data from our sample to create a best guess estimate of what the proportion is, or the mean, or anything. And then we create this interval around it saying, this is our best guess, but even though it may not be this, we're 95% confident that the true population parameter is within this range, or this interval. So let's take a look at that. Poll conducted, 8% of a random sample of 1,158 pet owners plan to dress up a pet for Halloween. So notice we only have 1,158, whereas we're looking at a population of pet owners in, I would guess, the United States, which is huge, millions and millions of people. So it seems strange that with only a little over 1,000 people, we can make this estimate for millions of people, and especially if we can do so with any accuracy. So we got 8% in our sample. So out of these 1,158, 8%, we could calculate that if we want, 0.08 times 1,158. This is the number of owners who did plan to dress up their pet. And so that is actually our best guess at the population proportion. So I'm going to type that in here as our estimated P, or estimated proportion. Now this would typically have that, it'd be P hat instead of estimated P, but just to remind you what this P stands for, and because I'm not quite sure how to do the hat in Excel, 8% is our best guess. And that will typically be the case. Whatever value you get in the sample for a statistic will be your best guess at the population parameter value. But we have this range, so is it plausible that 10% of all pet owners, now assuming that we have a truly random sample and we have a population that's much larger than this 1158, which I think we can assume here, it's at least 10 times is kind of the rule of thumb. Is it possible that 10%? Now it seems like certainly that would be yes, because 8% is not that far from 10%, and the fact that we only have 1,000 people out of potentially millions would seem that, yeah, that's probably pretty plausible. But let's create an interval and see. So in order to do that, we need the standard error. So remember, this is the standard deviation of all the sample proportions we would get if we did another sample of 1158, got a proportion. Did another sample of 1158, got a proportion. Then we plotted all these proportions. The mean of those would be the true proportion, but what we're looking for right now is trying to get the standard error, the standard deviation of those. And so what that is, it's the square root of, I'm going to put another bracket here because this is it's a fraction. In the top of the fraction, I have the estimated proportion times 1 minus the estimated proportion. And then that's all going to be over my sample size, which is 1,158 in this case. Okay, make sure I have everything there. And I didn't put a multiplication symbol in, so Excel was kind enough to add that in. So this is my standard error. Now what does that mean? Well, picture a normal distribution, so a bell-shaped curve. This is the middle, and this is the standard deviations that we're going out from that for a sample of this size. So remember, roughly one standard deviation to the left and to the right of our estimated mean, we would have 68% of the population, so 2/3 of the sample proportions. Or in this sense, because we're creating a confidence interval, because this isn't necessarily the exact population mean, what that means is we can be 67% confident that we're catching the true population proportion. But that's not really enough for what we want. We'd like to go at least a couple. Remember, 2 standard deviations will get us about 95% of the data. Specifically, so let's make this the lower estimate and the upper estimate. So to get exactly 95%, what we would do is go 1.96 times whatever this standard error is. And here we would go our proportion plus 1.96. So we're going 1.96 standard errors in each direction. And so we're 95% sure that the true population of pet owners who plan to dress up their pets is between 7.9 and 8%. So really, this is a pretty close estimate. Now there's some other things we should check. We should check that this sample size times p is at least 10, which it certainly is. It's well above 10. We should make sure this times 1 minus p, or 0.92, is at least 10, which it well is. It's over around 1,000. But with that, we know that we're pretty close. In fact, it's not plausible that 10% or 5% would dress up, because we're pretty confident it's within a little bit of 8%. There's a little bit of flex, but certainly not 5%, 10% are pretty unlikely, assuming a random sample again. Proportions 0.49 to 0.59 plausible values. No, these are way off. In fact, these are probably not. A 10% is very unlikely, potentially possible, especially because our sample might not have been truly random, or there could have been other issues. And 5%, it's again not likely, but possible. 0.49 to 0.59, there would have to be some incredibly serious errors in how the sampling was done or the data recorded. So this is not likely at all.